Welcome back to Complex Analysis. So last time we started the integral portion of our course, which again is going to take us to the end of the semester because integration, as we're going to see, has a lot of cool results and really fascinating things about it. But just recall that integration, at least in the complex land, is not so different, at least initially, to what we did back in calculus. It's kind of a mixture of Calc 1 and Calc 3. So remember now we're integrating over paths, which we're going to denote usually with a gamma. And the reason for this is, well, in complex land, if you have any two complex numbers, a and b, okay, we don't talk about intervals in the complex plane. We talk about paths, right? Because there's infinitely many ways of getting to one point to another. Okay, so we talk about integrating over paths now. But when it comes down to it, at least from a definitional standpoint, the way to integrate a complex function over a path is basically just doing what we do in Calc 1. So the integral of a function over a path we define to be, well, the integral from the starting point of your path to the end point of your path. F of, we plug in our path, and then multiply by the derivative of our path, and integrate that with respect to t. Okay? And again, remember, this is coming from basically your chain rule, or your U substitution, if you will. And in any case, this integral here that we ended up with, this is just a Calc 1 integral. So you kind of hope that, well, gamma is nice enough so that if you plug it into the function and then you multiply by its derivative, it's something that you can actually integrate. But in any case, this is a Calc 1 integral. So at least at this point, integrals really kind of combine Calc 3 and Calc 1. Kind of cool. So we're going to continue our integral journey, kind of like what we would do in calculus, and we're going to start with antiderivatives, which is sort of like your next step in integration. If you remember back in Calc 1, you talk about the integral with Riemann sums and the area underneath the curve and all that stuff, and then you probably do an integral using the definition, and you realize, oh, this is terrible, and then you get into the fundamental theorem of calculus, which makes our lives a whole lot easier, assuming you can find what's known as antiderivatives. So in any case, for complex analysis, we're going to sort of proceed the same way. Okay, so we're going to talk about antiderivatives for our complex valued functions, and then we're going to talk about the complex analog of the fundamental theorem of calculus. Okay, so let's sort of start there and recall, well, what is the fundamental theorem of calculus, which hopefully everyone remembers, because this is literally the biggest theorem we have in calculus. But the fundamental theorem of calculus says the following. Okay, so suppose that we have a continuous function from our interval, a, b, to the real numbers. And again, we want to make sure that this is continuous so that everything is true below. So then we can define a function capital F defined by capital F of x equal to the integral. So it's kind of a weird function, but f of x is equal to the integral from a to, and that's where your input goes. It's the upper bound of this integral, f of t dt. So this function that we create is differentiable, and if we take the derivative of capital F, we get little f of x. So a couple of thoughts or a couple of comments. First of all, this is usually called FTC Part 1. At least if you read a lot of calculus books, that's usually the first thing we call this. And really what this is doing is it's constructing an antiderivative for us, because capital F here, if you take the derivative of it, you get little f, and that's what an antiderivative is in a calculus sense, right? Which, by the way, is going to be similar in complex land. But in any case, Part A, or Part 1 of the fundamental theorem of calculus is basically constructing an antiderivative of your function. So this is kind of the brute force way, if you will, of finding an antiderivative. Usually when we find antiderivatives, we don't go through this definition. But in any case, that's what this first part's doing. Additionally, it's also giving us a sort of a tie between integration and differentiation. So if you kind of think about this theorem as such, so we have f of x here, and the first part of this theorem is saying if you take the derivative of this, you get little f of x. Okay. Essentially what that's saying, though, is if you take the derivative, because what is capital F in this theorem? It's an integral, right? Let me erase this part here. Capital F of x is an integral. So it's saying that if you take the derivative of your integral, whoops, and that should be an x right there, you get your function back. So it's kind of saying that derivatives undo integrals. So it's a way of branching differential calculus and integral calculus, at least in this direction. So the derivative of the integral gets you back to where you started with. So they're kind of like inverse processes of each other. Okay, so that was fundamental theorem of calculus part 1. Part 2 is the one you probably use the most in Calc 2. It says, so if f is any antiderivative, so part A constructs one, but part B is a little bit more general. It says if f is any antiderivative, and remember functions have infinitely many antiderivatives, if capital F is an antiderivative of little f, which means that the derivative of capital F is little f, then the definite integral from a to b of f of x dx is equal to, you just plug in the upper bound into your antiderivative and subtract, plug in your lower bound into your antiderivative. Okay, so this is Fundamental Theorem of Calculus Part 2. At least that's usually what it's called in books and in your class. And this is probably what you use the most, right? So what this is telling us is instead of having to use Riemann sums, basically the search or the problem of computing an integral comes down to, well, can you find an antiderivative? And if you can, you're good to go. Now, that's not an easy thing sometimes, as you guys hopefully remember from Calc 2. Some functions, it's a pain in the butt to find that antiderivative. Just sort of depends on what your function is. But in any case, Fundamental Theorem of Calculus says if you can find an antiderivative, then it's super easy to compute this integral. You just plug in your upper bound, your lower bound, subtract the two, call it a day. Okay. Another way of thinking about this, though, is sort of, again, if we think about the sort of the connection between differentiation and integration, this is sort of saying that if you integrate, so little f, okay, which remember, little f of x is also equal to the derivative of capital F. Okay. Basically what it's saying is that you not get capital F back, but you get some kind of number from it. So a way of thinking about the second part of the Fundamental Theorem of Calculus is sort of the opposite way. It's if you integrate a derivative, they cancel each other out. That's kind of what's going on here. We're integrating a derivative, and they sort of cancel each other out. Not in a super nice way like we had back in Fundamental Theorem of Calculus Part 1, but it's still that connection there. So there's a lot of good stuff with the Fundamental Theorem of Calculus, and hopefully you explored a little bit of that in calculus. But our goal is not to sort of dig up the past, but our goal is to sort of extend this into complex land. So that's what we're going to do pretty much throughout the video. Okay, so we're going to start with antiderivatives. So in complex land, antiderivatives mean the same thing as they do in complex land. So if f is holomorphic, so meaning it's differentiable, well, one part of that meaning is that it's differentiable in a region G, okay, and let's call the derivative little f, then we call capital F an antiderivative of f on G. Now in complex analysis, sometimes it's called not antiderivative, but primitive. Okay, so if you go on to grad school, you'll probably see that nomenclature, hear that nomenclature over antiderivative. We're going to stick mostly with antiderivatives because hopefully everyone's comfortable with that. In any case, though, an antiderivative is just a function such that if you take its derivative, you get the, whoops, jumping into calculus there, you get the lowercase function, quote unquote, back. Okay. Now in complex analysis, we do something that's probably a little bit different than you're used to in calculus. Notice that we say it's an antiderivative on some region. So this is going to be really important because we've explored that some functions don't have derivatives everywhere, so to speak. Okay, so whenever you talk about an antiderivative, you also have to say, well, what's it an antiderivative on? What's the sort of domain, if you will? Where is that antiderivative holomorphic on? So be careful about that. So when we say an antiderivative, usually we attach, well, where is it an antiderivative on? Okay, so let's look at some examples. So first of all, z squared over 2 is an antiderivative of z, since if you take the derivative, what do we get by the power rule? We just get z back. Okay, so this is actually an antiderivative of z on the entire complex plane. Remember, this is an entire function. Both of these are actually entire functions. They're differentiable everywhere. Okay. Now, another quick point I want to make is that, again, there's infinitely many antiderivatives. For instance, if we pick z squared over 2 plus I, okay, that's also an antiderivative because if we take the derivative, well, we're just going to get z plus 0, which is z. Okay, so just like in complex land, functions do have infinitely many antiderivatives if one exists. Okay, sine of z is an antiderivative of cosine of z on all of c. So again, we have entire functions here. Okay, and the reason for that is, well, what's the derivative of sine? Just like it is in calculus, it's cosine. Okay, minus cosine of z is an antiderivative of sine of z. And the reason for that is, well, if you take the derivative of minus cosine of z, just like in calculus, I don't know why I keep saying complex and calculus, maybe because they both start with c. In any case, if you take the derivative of minus cosine, you do get sine of z. Okay, so all these are examples of antiderivatives on c. Now, something with a little bit more kick to it. So the principal log is an antiderivative of 1 over z, not on all of c, because remember, this function is not continuous on the negative real axis, so we have to sort of chop that off. But in any case, the principal log is an antiderivative of 1 over z on c less the negative real axis there. Okay, and why is that? That's because, as we discussed, trying to count the videos a little while ago, the derivative of log, just like it is in calculus, is 1 over z. Boom. So a lot of the same ideas are going on in complex analysis that were back in calculus. Okay, we just have to be a little bit more careful with, well, what are you an antiderivative on? All right, so complex version of FTC part 2. So remember, FTC part 2 in calculus said, well, if you take the definite integral of a function, all you have to do is find an antiderivative, plug in the upper bound, plug in the lower bound, and subtract them. Okay, so we got a similar idea in complex analysis. So suppose G is a region and gamma is some piecewise smooth curve with some parameterization. Okay, so again, there's that calc 3 bit going on that starts at a, or time t equal to a, and ends at time t equal to b. So if we have a continuous function and f is any antiderivative of f on g, okay, then the integral of f over gamma is equal to, just like it says in calculus, you plug in your top bound into your path, plug that into your antiderivative, minus plug your bottom bound into your path, plug that into your antiderivative, subtract them, call it a day. Okay, so very similar to calculus, except remember, we're not integrating over intervals anymore. We're integrating over paths, so just don't forget. Okay, we don't just have f of b minus f of a, we actually have f of gamma of b minus f of gamma of a. Okay, but in spirit, it's the same idea. Okay, so let's prove that. So to prove this, let's talk about a couple of facts. So first of all, and this might seem like this is coming from outer space, but just bear with me here. So if we take the derivative with respect to t of this function right here, we get by the chain rule, so f prime of gamma of t times derivative of the inside by chain rule, gamma prime of t. Okay. Now remember, in this theorem, we're assuming that f is any antiderivative of little f, right? So what do we know about capital F prime? That's just f of gamma of t times gamma prime of t. Okay. So why did I bring that up? Well, let's go ahead and start to calculate f of gamma of t, or the integral of f over gamma. So the integral of f over gamma, so remember, by definition, this is equal to the integral from a to b, f of gamma of t times gamma prime of t, dt. Okay, so that's just by definition. That's what we talked about last video, pretty much exclusively, right? Well, now doing the substitution here, because we know f of gamma of t times the derivative of gamma of t is equal to d dt, f of gamma of t. And remember, this is a calc 1 integral, so we do have calc 1 FTC backing us up. We know this is equal to the integral from a to b, d dt, f of gamma of t dt. Okay, so using the fundamental theorem of calculus now, okay, because remember, if we integrate a derivative, we essentially get our function back. We do get f of, so plug in your bound, top bound into this. So it'll be f of gamma of b minus f of, plug in your lower bound, gamma of a. Okay, and here I'm going to be really explicit here. We are using FTC Part 2, the calculus version. So it's kind of cool. The calculus, fundamental theorem of calculus, actually gives us a way of giving us the fundamental theorem of calculus for complex analysis. Okay, but I want to make that clear there. We're not assuming this right here. We're actually using FTC Part 2, and the reason for that is, well, this is a Calc 1 integral. Okay, like we saw last time. Okay, so in any case, we do get a fundamental theorem of calculus Part 2 in complex land. Okay, that looks exactly, well, similar, barring this little path thing, to what we had back in calculus. So let's see an example of this. So let's go ahead and consider the function f of z equal to z cubed, so our cubic complex function, and let's look at the path 4 plus e to the it, where t is going from 0 to pi. So again, I just want to draw this, and I want to sort of drill this in your heads. What does this path look like? Because we're going to be looking at a lot of circles. Remember, this path is going to be a circle centered at 4. Okay. The radius is always the number that's in front of your exponential, so radius 1 in this case. And then this e to the it, that's going to give us our rotation. Now, what is the rotation? Well, it depends on what is our starting time and what's our ending time. So if we draw this, okay, so we're centered at 4. So 1, 2, 3, 4. Okay. So we're centered at the number 4, and t is going to be starting at 0. Okay, so let's see, we're radius 1, right? So radius 1 away from 4 would be 5. So we're starting here. Actually, I'm going to use a different color. So that's t equal to 0, and then we are going to pi, which means we'll end here at 3. Okay, so this is the path that we're integrating here. Okay, the circle centered at 4 of radius 1, where we're starting here at t equal to 0, and then we're rotating until t gets to pi, which would end us up at 3 there. And actually, I'm going to make that 5 green too. Okay. So let's go ahead and integrate this. So we could integrate this like we did last time by, well, plugging in our path into our function, multiplying that whole thing by the derivative of our path, and then plugging in our top bound, upper bound, or lower bound after doing a Calc 1 integral, right? But we're going to do this using the fundamental theorem of calculus. So quick note, I'm actually going to stick with green there, not vote. I mean, do vote, but note. An antiderivative of f here would be sorted by the reverse power rule. F of z equal to, so z to the 4th over 4 is an antiderivative of little f. Okay, so by the fundamental theorem of calculus, by fundamental theorem of, well, actually, it's not calculus anymore. We'll just say FTC of complex analysis. I don't know why I decided to, by the way, that's spelled wrong. I don't know why I decided to sort of abbreviate complex there. Anyway, so by the fundamental theorem of complex analysis, quote unquote. By the way, this isn't like the main theorem of complex analysis. We'll get to that later. But in any case, by the quote unquote fundamental theorem of complex analysis, part 2, we get that the integral over this gamma of f is equal to, so f of pi, f of gamma of pi, I should say, minus f of gamma of 0. Okay, so we have to figure out first what's gamma of pi, what's gamma of 0, and then whatever we get for that, we're going to plug it into our antiderivative, subtract them, call it a day. So gamma of pi is equal to 4 plus e to the I pi. Now, if we look at our picture there, we should see where that's at, because remember, we were going this way. This is going to give us 3. Or just remember, e to the I pi, that's also cosine of pi plus I sine of pi. And if you remember your trig, sine of pi is 0, cosine of pi is -1, so 4 plus -1 is 3. All right, gamma of 0 similarly is 4 plus e to the, well, 0, which just like in real land, this is 4 plus 1, which is 5. Okay, so this is going to give us f of 5 minus f of 3, okay, which is equal to, so now let's plug that into our antiderivative, 5 to the 4th, which I do not know off the top of my head. What's 25 times 25? Big number. Minus, if we plug in 3, we're going to get 3 to the 4th over 4. That's 81. Anyway, we're going to leave it at that. Okay, so we get 5 to the 4th over 4 minus 3 to the 4th over 4 using the fundamental theorem of calculus. So again, a lot easier than what we were doing last time. I don't know about easier, but at least it was, as long as you can find that antiderivative, you're pretty much good to go. Okay. Now, a quick note about this, because we are going to see something called a closed path soon. If we let t go from, instead of 0 to pi, if we let t go from 0 to 2 pi, whoops, not 2m, 2 pi, essentially we would be integrating over this full circle here. Okay. And what we would end up seeing is that we do get 0. Okay. So if t was going from 0 to 2 pi, the integral would have been 0. Okay, now the way to see that, well, if you plug in, so our calculation would essentially have been the same, except, let's see, 0. Now our lower bound would have been, or our upper bound, I should say, would be 2 pi, and so we'd have gotten 3 again. So these would have canceled each other out. But we're going to see this idea a lot. This idea, if you integrate over a closed path, you get 0. We're going to see this, and by closed path, I mean a path that starts and ends at the same place. We're going to be studying those a lot. Now, it's not always 0, by the way, but it depends on sort of the function that you're looking at. But we're going to see that idea a lot, so I think it's worth mentioning that, well, if we were integrating over a slightly different path, we would have gotten something different. All right, so let's formalize our discussion from the last problem. So suppose G is an open set, and let's suppose that gamma is some kind of piecewise smooth closed. And remember, closed, we mean the start. So the starting point is actually equal to the end point. Okay, so you start and end at the same place. So suppose that we have this piecewise smooth closed path that's contained in G, and let's suppose that f is continuous on G and has an antiderivative on G. So this is really, really important. Your antiderivative has to be on all of G there. Then the integral of f over your path is actually equal to 0. Okay? Now the proof for this is really, really simple. It just comes from our complex version of FTC part 2. The integral gamma of f is defined to, or will be by the, again, our complex version of FTC part 2. It's f of, where f is our antiderivative, capital F of gamma of b minus capital F of gamma of a. But if you're dealing with a closed path, meaning that your start is equal to your end, that means that the insides here are actually equal. Okay, so that means that these two numbers will actually cancel out, giving you 0. Okay. Now, a couple of important things. This isn't saying that if you integrate over any closed path, your integral is automatically 0. That's not what this is saying. It's only 0 if you have these conditions met. So first of all, G has to be open, your function has to be continuous, and has an antiderivative on all of G. Okay, if there's a point missing there, maybe there's some point where you blow up, or you divide by 0 or something. This isn't going to work. Okay. So just be careful of that. Don't just think that, oh, if it's a closed path, your integral is automatically 0. It's kind of a big thing in complex analysis. We have to be careful about that. Okay. In any case, this useful result here also gives us a really, really cool way of sort of telling us whether or not a function actually has an antiderivative on G. So if you take the contrapositive of the statement, this says that if there exists a path in G for which the integral over that path of f is not 0, then you know right away that your function does not have an antiderivative on G. Okay? So this is a really, really nice way of determining whether or not a function has an antiderivative by looking at it through this sort of this backwards lens. Okay, so let's look at this through an example. Let's consider the function 1 over z, and let's let gamma be the unit circle. Okay, so by the exercise that I recommended at the end of the last video, we'll have that the integral of f over gamma, which is the integral of 1 over z, okay, dz. So remember, by the exercise I recommended, this is actually going to be 2 pi I. Okay. So we know right off the bat that 1 over z doesn't have an antiderivative on any subset that contains the unit circle. Okay. And remember, that's why we made that little stink about the antiderivative being the principal log, where we had to cut off the negative real axis. That's a classic example of why you have to be really, really careful about where your antiderivatives are located. Okay. So this tells us no antiderivative on any region containing the unit circle. And the reason for that is, well, if you do integrate the unit circle, you get 2 pi I, which hopefully everyone believes 2 pi I is not equal to 0, so that means that we don't have an antiderivative by our corollary here. Okay. So again, this result is very, very helpful when you want to determine whether or not a function has an antiderivative on a certain region. Okay, so wrapping up the video, we're going to talk about the analog to the first part of the fundamental theorem of calculus, which again is sort of constructing that antiderivative using brute force. And so we have, again, a similar result. So suppose G is a region, and let Z naught be in G. And suppose f is a continuous function such that the integral of f over gamma is equal to 0 for any closed piecewise smooth map, or smooth path, gamma that's contained in G. So very, very different from our calculus, fundamental theorem of calculus part 1. Okay, because again, we don't have paths or anything in Calc 1. So we have a slightly beefier assumption here. We're not just assuming that f is continuous, but we're assuming that the integral of f is over any closed path is 0. Okay. So if these conditions are met, then we know that the function, which we're calling capital F, defined by this right here, okay? So it's we're defining f of z to be the integral of f over this gamma of z, where gamma of z is any piecewise smooth path in G that starts at z naught, which is our point that we have in our assumption here, and ends at z, okay? So this is an antiderivative of f on G, meaning if you take the derivative of this integral function, you get little f back. Okay, so similar to what we had back in Calc 1, except again, we're in a complex setting, meaning we're going to have paths, and we have slightly more strict assumptions that'll allow us to build this antiderivative function. All right. So last couple of words. So essentially what we've been doing with integrals at this point is we've been doing basically what we did back in Calc 1 and Calc 2 and in Calc 3, right? And by Calc 3, I mean we're using paths, and then Calc 1, Calc 2, we're integrating using fundamental theorem of calculus. But that's where we're going to actually stop with the calculus stuff. We're actually going to shift gears now and take a really, really different approach to integrals, and we're going to use topology to do so.